Thanks, Alex, and thanks everyone for showing up today. We're excited to talk to you a little bit about some of the work we've been doing to develop modeling frameworks to be able to characterize the distribution and spread of aquatic invasive species. And before I get started, I want to introduce briefly the rest of our research team. So this project is funded with co-PI Dan Larkin, who's a faculty member in FWCB, Sabby Berra, who was a PhD student in statistics and now moved on to National Institutes of Health, Alex Bajcz, who was a postdoc on the project, now Macer's quantitative ecologist, and Wes Glisson, who was a research fellow and now at Washington Department of Ecology. So you can see a lot of our research team has sort of moved on, but we're still making progress on this, and excited to kind of tell you a little bit about the work we've been doing today. So we have two different aspects of this project that we'll be talking about. The first is some work that's still ongoing, where we're trying to develop a landscape level model for the distribution and spread of Eurasian water milfoil in Minnesota lakes. I'll be briefly giving you an introduction to that part of the project. And then the second sub-project is one that Alex is going to present, discussing modeling efforts to describe the within-lake distribution of starry stonewort in Minnesota and Wisconsin lakes. So for this first project, many of you probably know better than I. My background's in statistics and mathematical modeling. Eurasian water milfoil, very important species. It's invasive here in North America, native to Europe, Asia, and North Africa. And you can see it grows in these dense mats, which can have significant impacts on native plant species, recreational activities, and property values. And there's been quite a bit of work by Macer Research and other researchers and others to try and understand the distribution of EWM. Here's some data and some results from a Macer-funded project looking at different factors related to the distribution of EWM. The plot on the left shows, with the red dots, different lakes that we know have EWM, and the blue dots are lakes that have been sampled, but for which we have not detected EWM yet. And so Thomas et al. Looked for different factors that were correlated with the distribution of EWM, and some of the results are given here. The larger the bar, the more important the variable in terms of the association with presence of EWM in lakes. You can see the most important thing that they found was that an autocovariate was important, and that basically says if your neighboring lakes are infested with EWM, there's a good chance that you are as well. They looked at lots of other predictors, but the main thing is they were just looking at associations here, and we're trying to do something a little bit different. We're trying to develop a mechanistic model where we can really understand how these different factors influence the spread of EWM. So we're trying to do that by integrating multiple data sources. One is the Minnesota DNR's list of infested waters, using data from 2007 to 2018, which includes the first date that EWM was known to have been detected in Minnesota lakes. We're going to also include over 3,000 point intercept surveys on over 1,500 lakes. And if you don't know what a point intercept survey is, it's essentially a systematic survey of the littoral zone of a lake, shown here on the right side. And Alex is going to be talking more about point intercept surveys in his part of this project. Lastly, we're trying to integrate information on boater movements from watercraft inspection data collected between 2014 and 2017. So we've got several different data sources, and the way we're trying to develop this model is we're going to have two different important components. The first is a biological process model where we're trying to model the mechanisms of spread, largely assumed to be from boater movements, and then also model establishment within lakes and factors that might influence establishment given that EWM shows up on a boat from an infested lake. So we've got model components that capture the probability that EWM was present at the start of our data set in 2007, and then we're going to model the probability that uninfested lakes that weren't infested in 2007, become infested each year. On top of that, we're going to try and account for the ways that we collect our data. So we're going to have different observation models that we overlay on top of that biological process model. And those observation models are going to try and account for things like imperfect detection, sampling biases that are unique to these data sets. So as I mentioned, I'm a statistician, so I think in terms of math as a really precise way of describing what we did. I will also try and give a feel for what that math means biologically. Here we're going to model the presence absence of EWM in each year using these called indicator variables, ZIT, which will take a value of 1 if a lake is infested in year T and 0 otherwise. And we're going to model those presence absence values in the first year of our data set using what's called the Bernoulli distribution. You can think of this as like flipping a coin, where the probability of a head, or in this case, the probability a lake is infested, is determined by this parameter gamma I. And that gamma I depends on things like, depends on within lake characteristics, things like the size of the lake and its Secchi depth. We're then going to consider a series of assumptions when modeling how lakes may transition from uninfested to infested. We're going to assume that new infestations arise solely from boats that come from previously infested lakes. We're not going to assume that we know all of those infested lakes. We're going to try and model that process using that biological process model. We're going to assume that each boat arriving from an infested lake serves as an independent potential AIS transmission event. And we're going to assume that the probability that a boat coming from an infested lake results in a new establishment of AIS depends on a lake's habitat suitability and may vary annually due to things like changes in education and enforcement. Lastly, we're going to assume that once a lake has become infested, it stays infested. It's really hard to eradicate EWM, so we're unfortunately going to make that assumption as well. These assumptions can then be translated into equations and a statistical model. So we're going to assume now, or we're going to model the indicators for whether a lake is infested in other years, again as a coin flip. And the probability of infestation is given by this information in the parentheses here. You can see if a lake was infested in the previous year, it's going to stay infested. That's where that assumption comes into play. If it wasn't infested in the previous year, then there's a certain probability it's going to transition. And if you take those other assumptions and work out the probabilities, you get an equation that looks like this. This is the transition probability. The probability a lake transitions is essentially 1 minus the probability that it doesn't transition anytime that a boat comes from an infested lake. So this little psi here captures our establishment probabilities, which reflect habitat suitability. We're going to model those as a function of within lake predictors, things like lake size and Secchi depth, and allow them to vary over years. And this term up here is essentially trying to capture how many boats are coming into the lake from other lakes that already have EWM. So the Z, again, is an indicator for whether a lake has EWM or not, and the U here is capturing boater movements. So we have a part of our model that is trying to capture how many boats are moving between lakes. We, again, are going to assume a particular statistical distribution for those number of boats going between lakes, and the mean of that distribution is going to depend on things like the distance between the lakes and within lake characteristics. So there's Secchi depth and Secchi depth squared, so that measures of water clarity, as well as how popular the lakes may be. So their distance to nearest city, distance to the nearest highway, population density in the county that the lake sits in. So together, those parts capture our biological process model, and we're going to overlay on that observation models that capture important characteristics of how we are actually collecting our data on known presence and absence in different lakes. So for our point intercept sampling, we're going to assume that the number of positive detections is given by a binomial distribution. So you can think about this as flipping a coin many times and counting the number of heads. Here we're counting the number of detections on these point intercept surveys. And those number of detections will depend on the number of sample locations we have, We're gonna assume we only get detections if EWM is actually present. So that's why the ZITs show up here. We're gonna assume that there's no false positives. And then we're gonna assume that lakes have their own detection probabilities, and we're gonna model those. Those are given by the PIs, these parameters here. And then in terms of the infested waters database, we're going to assume that once a lake enters the database, it remains listed. So these WITs are going to keep track of when lakes first enter the DNR's database of infested waters. Once they're there, we're going to assume they're always there. If they weren't there in the previous year, we're going to assume that if EWM is detected via point intercept sampling survey, that it's going to show up in that data set. And then we're going to assume that if it wasn't there in the previous year and we did not detect it in a point intercept survey, that there's still some chance that we're going to find out that it has EWM as long as EWM is actually present in the lake. So these are going to be other opportunistic detections, and we're going to model the probability that we opportunistically detect EWM in a lake as depending on things like, again, the distance to the nearest city, distance to the nearest highway, population density, and lake size. So again, we're going to assume that lakes that get more use are going to have more of a chance of detecting EWM, even if they're not surveyed using point intercept surveys. So that's the modeling framework we're trying to develop. We've been able to fit, we're kind of sequentially building up to this model. We've been able to fit models that capture most of these characteristics, and we're still working on the computer code to try and fit the full model, but we can give a sense for some preliminary results based on some simpler models that we fit. And essentially, we can say pretty confidently that boater movement and lake connectivity are going to matter, and they matter a lot. The lake connections are strongest for lakes that are near each other. That's not too surprising. And for lakes with moderate values of Secchi depth. And then we're also finding that observation biases are really important. So we're trying to account for those. We're finding that EWM, when present, it's more likely to be reported in lakes that are near cities, highways, and counties with higher population density. So again, this is still a little bit of work in progress. But I want to highlight why we're doing this and the idea and the potential benefits to developing a mechanistic modeling framework. And that is, we're hoping to better capture the factors driving the presence and spread of EWM by actually modeling those mechanisms of spread versus just trying to model associations with different predictor variables. And if we're able to do that, we should be able to have better forecasts of risk by taking into account those mechanisms. So that's the end of my portion of the talk. I want to thank all of you and thank our funders and partners. I'm going to turn over the talk to Alex here and let him talk about the other part of our work.
Hello, everybody. I'm super excited to be talking about this work. This was work that was led by me, facilitated by John Danlark and Wes Gleason, as well as Jeffrey Dozer, who wrote the R package SP occupancy that we used as a part of this work. I've entitled this portion of the talk, Seek and Ye Shall Find, though I should clarify, no, not that ye. He's not going to help us find anything. This part of the talk is all about sort of improving how we go looking for a stealthy aquatic invader, in this particular case, starry stonewort. I'll start off with a bit of an adage here, and that's that an ounce of prevention is often worth more than a pound of cure. And in the context of AIS, what I mean by that is that eradication or even control, as John was saying, of an established AIS population is really hard. So preventing AIS establishment is obviously our best option, but that too is often hard. So early detection when control may still be possible is a really good next option. But how do you actually go about trying to find something that is rare early enough to make a difference without sort of driving yourself crazy in the process? That's the real challenge here. And us modelers would say that the answer to that is, well, modeling, right? Specifically, we might say, go out and find the spots where the species already lives and ask, what are those spots like? Are there patterns to what those spots are like? Because if so, those patterns must indicate what the species like, and we should just go looking in other likable spots. And though it's a simplification, that's sort of the essence behind a whole class of modeling called habitat suitability modeling. But life is rarely quite that simple. There's problems to this kind of modeling. First off, how do you get enough data to find patterns if the species you're trying to find is rare? That's a bit of a paradox, right? Also, what if where a species is or isn't is about much more than just what it likes? And spoiler alert, that's certainly true with AIS. And that's because by definition, AIS are still spreading in the area that they are spreading within. So they haven't seen everything yet. So where they are may be more about where they can get to and how quickly than what they actually like. And then there's the issue of what if you can't trust your absences in your data? Can you miss something that you're looking for even when it's there? And the answer is yeah, unfortunately you can. So how do we go about trying to tackle these challenges? Well, first off, we went out and found partners who had lots of valuable, systematically collected data that was actually gathered for a different purpose that we could use here, since data from invasive monitoring often doesn't work super well in modeling for invasive monitoring. We then built a model using those data, incorporating the BAM framework, more on what that is in a second. And then specifically, we chose sort of a relative of habitat suitability modeling called occupancy modeling to do this work using the SP occupancy package in R. And one of the reasons for that is that it handles some of these complicated challenges like spatial gluiness and imperfect detection right out of the box, which is pretty amazing. I'll talk about how it does that towards the end. A little context here. The species in question we're going to be talking about is starry stonewort, or starry for short. It's a member of the Cariaceae family. It's been in our region since about 2014 at least, and it's still actively spreading here. A few years back, then Macerc grad fellow Mike Verhoeven started hatching a plan to learn more about AIS like starry. Specifically, he knew that there were many dozens of groups in the state and beyond that were regularly conducting these PI or point to intercept aquatic plant surveys every year. These are sort of systematic looks at a lake's plant community. You go out to all these spots on a grid in the lake, you throw a rake overboard, you reel it in, you see what plants are on it, and so you get a cataloging of essentially what is where and how abundant it is and where things aren't too. And he and Wes Glisson thought, you know, if we could collect all these surveys together, we might be able to leverage them in some really cool ways, such as being able to make an occupancy model. So they started asking folks from several different organizations and businesses that were conducting these surveys for their data, and then sort of painstakingly compiling them, since every one of these data sets looks different. And the result of their hard work is a truly massive data set from starry infested lakes. It spans 8 years, 23 different lakes here in Wisconsin and Minnesota, and almost 23,000 observations of where starry was or wasn't. This sort of automatically included some biotic data, right? Like what other plants were at those same locations besides maybe starry. We then added to that data set some abiotic data, such as depth and the amount of mixing you'd expect in those spots, as well as actually movement related data, like how close is each spot to the nearest boat launch at the same lake. And I've highlighted the B, A, and M here because this is the BAM framework that I was talking about earlier. If where a species is found or not is not just about what that species likes, but also about who else is there and whether the species in question can actually get there or not, then you need to have those factors in your model too if you want to predict that species' location or occupancy well. So that's what we were trying to do here. Now, before showing you what our model has found, because I've got some results to share here, I want us to quickly practice reading the types of maps I'm going to be showing from here on out, because they're a bit complex. So this is a map of Silver Lake in Wisconsin. The X and Y here are lat-long coordinates, so westing and northing here. The lake's outline is shown in black, and if there are any access points on that lake for motorized boats, those are marked with yellow diamonds. So there is one public access up here. That's what the B stands for. If it were a V, that would be a private or business-run access instead. Beyond that, there are three factors that I want us to consider on each of these maps. And the first of them is point shape. So the squares in dark red here are locations that we know starry stonewort is present because we've already detected it there at least once. The circles, meanwhile, are predicted occupancy probabilities from our model. And here's where color comes in. If you have warm colors or redder colors, that indicates the model thinks there's a high likelihood starry stonewort is there. Cool blue colors mean low probabilities. And then you'll notice that the points also vary in size. Size maps to something else. Large dots here are always more of something. Small dots are always less of something. And here that actually has to do with uncertainty. So the model is feeling very confident about its probabilities when the points are small, not so confident when the points are large. So if that all didn't sink in, no worries. We'll have a lot more of these maps to look at. So we'll get more practice as we go. And you can, of course, ask me about it in the Q&A. All right, let's start by looking at a discussion of abiotic factors. What is it that Starry likes? Well, according to our model, both depth and fetch matter here, but it's complicated because our model had an interaction term between these variables that ended up being significant. So we need to unpack that, and we can do that using what's called a tile plot. So on this tile plot, as we move from left to right, we're moving from very shallow depths to very deep depths, though we're still in the littoral zone, so not super duper deep. As we move from the top down here, we're going from very low fetches, so low levels of wind mixing, to very high fetches, high levels of wind mixing. And we can sort of like walk down any direction in this tile plot to see what's happening. So let's go ahead and ignore the numbers and just look at the colors. Warm colors here, reds mean high probabilities that the model thinks Starry is going to be there. Colds mean low probabilities, just the same as on the map. And if we move from left to right here, what we can see is that shallow depths are almost always better. Actually, they are always better for Starry than deeper depths are. We go from warm to cold here as we move from left to right. As we move from the top down, we see cooler colors graduating into warmer colors, indicating that actually in general, more mixing or a higher fetch seems to be better for Starry. But what's really interesting is that actually isn't strictly true. And we can see that if we look at the corners. It turns out that when depth is low, but mixing is high, that's actually fantastic for Starry. That's supposed to be the highest probability of occupancy. But when depth is high and mixing is high, that seems to actually be terrible for Starry here. So we can summarize this by saying, you know, greater depth is always bad. Going from left to right here, you're always getting cooler colors, but it's even a starker transition when mixing is high. For fetch is actually great at shallow depths, but terrible at deep depths is what we're learning here. So that's that interaction effect in action. And now that's tricky to follow. We can actually see these patterns on a map by examining two maps from Long Lake in Wisconsin. So on this first map, we have depth mapped to point size. So the smaller dots are shallower depths and the larger dots are deeper depths. And what we can sort of readily see, hopefully, is that all the small points are along the shore, as you might imagine. That's also where all the warm colors are, is along the shore. And where all the infested points are is also along the shore. So that's sort of evidence of depth mattering, that shallow depths are generally better. Now, if we transition to looking at fetch, now we have fetch mapped here so that larger points are higher fetch values. And the pattern here is a little bit harder to see. So I'm going to have us zoom in on some pairs of dots to see it. So we have a pair of points here. This is a shallow region of the lake. It's near other infested points. But this point here is actually larger than this point. It has a higher fetch. And you'll notice it also has the warmer probability color. So this is evidence that higher fetch is good when you have a shallow location. Now we can zoom in on these 2 points. This is a deeper region of the lake, still near other infested points, but this has the higher fetch, and it actually has the cooler color in this case, although that is a little bit hard to see here. So higher fetch bad when you're talking about a deep region, higher fetch good when you're talking about a shallower region. And this is the benefit of modeling, right? You can detect patterns like this that would otherwise be hard for us to detect by eye. All right, now let's go on to moving into movement-related factors. As we might predict, proximity to a boat axis, it was a strong predictor of occupancy here. So this is Little Cedar Lake in Wisconsin. Here's the one axis point down here. And you can see that most of the known infestations, as well as most of the warmer colors here, are all clustered right around this axis point. So that was kind of expected. However, not so fast. How do we know that that pattern is actually about movement and not about preferences, right? Maybe axes are where boats are bringing in new starry infestations to lakes, but that's not the only possibility, right? Axis areas could also somehow be environmentally preferable for starry too, right? Which is it? Well, we actually could help answer that question with our model because we ran a variant of our model that included an interaction between the distance to the nearest access point and time. So this is very close to an axis. This is very far away from the nearest axis. This is right after an infestation was found. This was many years after. And as we check this out, we can see that as you move away from an axis, the occupancy likelihood goes down. And as you move forward in time, the occupancy probability goes up as an invasion sort of spreads. What's really interesting here, though, is what's happening over time. If you look very soon after an invasion, this pattern, this trend is very stark. All the occupancy is right near the nearest axis, and it goes down very slowly after that. But if we move forward in time, you can see that all these colors down here are pretty much warm and pretty much the same number. That relationship sort of just completely flattens out, which is exactly what you would expect if access areas are just sort of ho-hum for Starry. They're just sort of a foothold that Starry gets into, but then spreads out away from as soon as it has an opportunity to do that. This might actually be good news if it's true. If places where Starry tends to start out in a lake are just sort of meh for it, it might mean that eradicating them there would be easier, assuming we can find them in time. So that's an interesting result for that reason. And then lastly, we might ask, does it matter whether the nearest access to a spot is public or private? And the answer here is a very qualified maybe. So the coefficient in our model here was positive. So it indicates a higher occupancy near private business run accesses. And we can actually see this pattern very clearly at Wind Lake in Wisconsin. You've got two accesses here, one public access where things are very quiet, and one private access where things are anything but private. So that's possibly that relationship being seen. However, I can't stress this enough. This term was not significant statistically. So 0 lies just barely inside of the 95% credible interval. So there's some evidence here to suggest this relationship may not hold or is shaky. So I can say that there is inconsistency here. I could have put up a different lake that actually showed the opposite pattern. They do exist. The challenge here that we're really running into is there's just not a lot of lakes in our data set where you have both types of accesses. So it makes it a little harder to make a really strong direct comparison. So there's something here, but it's sloppy, and it's probably something that we need to investigate more specifically. All right, I'll wrap up by very briefly describing how our model solves two big problems that I raised earlier. And the first one has to do with gluiness. When Starry enters a new lake, it's going to spread outward from wherever it happened to start, even if those spots are great or not around it, right? In other words, if you were a spot in a lake and some of your neighbors were already infested, you're likelier to get infested too, thanks to proximity, even if you're not a particularly good spot, right? So that's more just about spatial luck in a way than it is to do with preference. And SP occupancy actually accounts for this in a very cool way. It adds in this variable called W. And what W is basically this weighted average of the occupancy probabilities of every point's 15 nearest neighbors. In other words, when a spot's neighbors are sick, W is going to go up, and we're going to be more likely to predict that that spot is sick too. And we can actually see W's influence here at Pine Lake in Wisconsin. So I want us to hone in here on the points in the center of the lake. These are spots that the model otherwise would think was pretty lousy. It's deep, it's high fetch, it's far from the nearest accesses. But there's just happens to be a couple of sick points here, which means W is going to go up, which means we're going to get slightly higher probabilities of occupancy here than we otherwise would. This is cool for two reasons. First, the math of making every guess you make dependent upon every other guess you're making is really tricky. So the fact that SP occupancy just sort of does this out of the box is incredible. It's also cool, though, because it helps prevent the model from confusing local spread with preference more than it ought to, right? Don't overvalue these spots as being good spots. Maybe they just happen to be near a spot that kind of got lucky, right? The other problem had to do with imperfect detection, right? Sometimes you miss stuff even though it's there. Our model actually estimated this specifically. It thought you only had about a 63% chance of actually finding Starry with a single sample in a place with average plant cover. So not bad, but not great. And if you jack up the plant cover, that probability actually goes down quite a bit. It goes down to 38% if your rakes come back looking like this, for example. So this confirms that starry can be tricky to find and that we might need to look harder for it than we do now sometimes, or in some contexts. But it is also cool, by incorporating this into the model, it allowed the model to guess that some spots really are occupied, even though we don't even know that yet. So it allows those sort of educated guesses to contribute to the pattern finding in ways that absences don't normally contribute, which I think is very neat. So to sum up really briefly here, our model is cool, it works well, it aligns with what we tended to know already about starry. It tells us depth matters and mixing matters, and local and between lake movement processes matter too. It also tells us that while low depth, high mixing areas are great for starry, access areas aren't special by themselves, and that may actually be good news. We also confirm that starry is tricky to find, but in ways we can actually maybe plan around now. And then lastly, it tells us that accesses do differ a lot in risk from each other as potential places for infestation to start. Type here, public versus private, isn't useless, but it's sloppy, and we could probably do much better if we actually studied this differential risk of accesses explicitly, which would probably be a really fruitful next step. So to those of you out there in the audience maybe who contributed data to this project, thank you so much. It would not have been possible without you, and I hope you'll continue to support our work by submitting your PI survey data through our app PI Charter. And then, of course, thank you to all of our funders as well. And John and I would now be happy to take questions.
Of the 3 types of milfoil in Minnesota lakes, Eurasian water milfoil, hybrid milfoil, and northern or native milfoil, John, in your study, is that limited only to Eurasian water milfoil?
It is. It's currently limited to Eurasian water milfoil, and the modeling framework in principle could be applied to other species, but currently that's been our focus.
Next question is, how does your Eurasian water milfoil modeling approach differ from others that have been conducted by MACERC staff?
Yeah, so the big thing is we're trying to capture mechanisms. So there's lots of these modeling efforts that are just looking at associations, and those associations can be driven by lots of different things. It could be sampling biases, it could be a confounding variable, but we're trying to get closer to understanding mechanisms. And maybe I could share my screen again. Alex, can I share screen again? So just to give a feel for that, I really like, there's this paper that I think really illustrates this point well. It's published in Global Ecology and Biogeography. These species distribution models that are often constructed to try and understand what factors are associated with distributions are really popular. This paper highlights some of the issues with that. Oftentimes, we just take predictors, whatever we have available to us. Like in here, they were modeling a species as a function of climate and topography. And they constructed a model using that, and it predicted really well. They found these close associations between climate and topography and the species distribution. But then they took paintings, and they took those paintings and stretched them over the same study area. Those paintings have spatial clustering patterns in them. And they use the paintings to develop predictors, which clearly are not related at all to the distribution of the species. And then they, again, use these same sort of correlative modeling approaches, and they actually found they did slightly better with the paintings than the climate topography predictors. So this is just kind of one of those warnings that it's really easy to build species distribution models to look at associations. We're trying to do something a little more complicated by trying to model the mechanisms, but by doing so, we hope to actually get a little better understanding of how those factors are related to distribution and spread. Hopefully that helps.
That's great, thank you. Next question is, do you know of any better detection using underwater drones or AI?
Myself, I don't know if this is specific to Starry or EWM, or I don't know. Obviously, underwater sampling can be more effective for finding aquatic invasive species, but it's pretty expensive, is my understanding, and intensive to do. And I don't have a good handle on that literature. Alex, I don't know if you know of anything in that
Other
realm.
than that, there are other MASERC projects that are focused on this kind of very question. Yeah, I don't either. And I think that's part of something we've sort of put a pin in to say this is something we need to understand better.
Next question is in the first project, I think this means, John, in your presentation, why was the infestation status stopped in 2018 and would results change with additional years?
Good question. So, I mean, that partly reflects when this project started. Those were data that we had available to us. The point intercept survey data went through that time period. And our progress has been slowed a little bit because, like I showed at the start of the presentation, the student that was doing the majority of the modeling on that part of the project, he was a PhD student who ended up getting a different research assistantship halfway through the project. So we lost his ability, and then he came back for a short stint this summer, but he's gone now again. So part of it just is an artifact of when we started. Once we can get the framework up and running, it should be easy to add additional years to the data set. So,
Alex, this question is for you. Why do you think private access points were associated with more starry stone work?
Yeah, thank you. I was noticing these questions come in, and I'm not surprised. I think we had a sense that we might, I don't know, stir up some trouble here by putting this variable in our model and then finding that it might be influential. Public versus private is a really crude differentiator. I just want to point that out, that like, in essence, besides who is sort of managing or running the access point, there may be a wide variety of differences between them. And, it could have something to do with traffic. It could have something to do with interventions, as one of the questionnaires brought up. But the cause and effect here actually could be something entirely different. Like, what if private accesses tend to be placed in locations in a lake that happen to be more favorable for starry? That would be something that our model could not differentiate between, right? I mean, in theory, at least, accesses are not themselves distributed randomly around a lake, right? So it might actually be that just public accesses get the best spots or whatever, and thus private accesses end up in less favorable spots in terms of not becoming infested with starry. But I think all we really discovered here, remembering that there's only 23 lakes in our data set and many don't even have a private access at all, I think what we realized is we really need to go in and ask, what does make an access risky? Sediment, location, embayment, intervention level, all these factors that might make it more likely for starry to end up in one place versus another. We need to sort of ask that explicitly, and we probably need to do it with a species for which we have a lot more data. So there's been sort of talk about trying to do this exact same kind of model again, but for a species like Eurasian water milfoil, where we'd have 500 lakes or something worth of data. And then I think maybe we'd be able to start teasing apart, what is it about an access that might make it more or less risky.
Great, thank you. Next question is, do you think there's a correlation between private boat access and lack of inspection points? This is probably a follow-up, even though the data may not show it yet in terms of introduction to starry.
Yeah, I will sort of ask the audience to see if they think I answered these next three questions to their satisfaction, because I think they're all pretty much related. I mean, Jeff, that would certainly be a possible implication, right? But even just trying to play devil's advocate, I could probably come up with 5 or 6 other possible explanations, right? Including the one that I gave you, which is actually that maybe just private accesses get unlucky about where they get to be located in the first place. And that would be something that our model couldn't differentiate between. So we presented that work on access type, but put some asterisks over it, because as we would say, it's crude, and it's not useless, it's helpful, but we need to probably tackle that question more specifically if we really want to know the answer.
And did you want to follow up on the third one, Alex, or
if they have
mostly covered?
if they have some aspect that they feel like I haven't quite gotten yet, they're more than welcome to throw it in there. But I don't want to beat a dead horse here if that's
Yeah.
what I'm doing.
Thank you to both John and Alex for presenting.